Ladies and gentlemen, we welcome all of us once again to this session. Today is day 5 of the FAST4Future Summer School on Space Technology and Applications. And today we are going to listen to a very important aspect of our lecture, which is on remote sensing. And we have an expert with us that is going to talk to us on the topic. Today, we are going to listen to one of us, Dr. Daniel Oko. Dr. Daniel Oko has his PhD in space science, and at the moment, he is a research fellow at the Technical University of Kenya in Nairobi, where he has been for some time working on space science. So for this session, Dan, please, we are going to have 2 sessions. We will have the first 1 hour of a continuous lecture, and then about 10 to 15 minutes of interaction, after which we will break out. There will be a break for about 30 minutes, and then we bounce back for the second segment to complete. Probably we are going to end around by 2 p.m. of my time. So that's how it will be. So for now, we are going to take for the first 1 hour, after which we interact with the participants by way of questions, comments, and clarifications. And then after the break, we bounce back for the second session. So Dan, it is over to you. You now have the floor for the presentation. Thank you.
Okay, thank you, Professor Finbar. Yeah, can you see my screen?
Yes.
Okay.
I can see
and
the
you
screen.
Okay, thank you so much. So welcome everyone, and let me make it in slide. Okay. Is it in slide presentation mode
it's
now?
now presentation mode. Yeah.
Okay. So thank you and welcome everyone to this class. I will try as much as possible to make it very interactive. And yeah, so I would prefer not to run it at like continuously as a talk, but rather if you have any question at any stage, you can just indicate by raising hand, and then I would allow you talk, and then we continue. So that is the mode I prefer it takes, so that it doesn't go a lot on understanding parts that are not understood.
Okay,
It
I think
can
that
make
is good.
everything. Yeah.
Thank you.
Okay. Yeah. So in the course of this presentation, I will be talking 3 main aspects. So I'll be looking at an introduction to remote sensing. Then I will talk a bit about satellites, and then deep more into the GNSS, which we're going to talk in the next session. So for this first hour, we're going to concentrate on this part, and then for the next hour after the break, we would look at applications of remote sensing in space science, and then also for AI, artificial intelligence and machine learning applications. Yeah. So we wanted to you. Okay. Yeah, so let's look what exactly remote sensing is. I use this illustration of a remote control because almost every one of us would have seen it. So when we think of the remote control, we think of like the television, where in those days, where before the invention of remote controls, we normally needed to press the buttons on the television. So we needed to make physical interaction, physical contact with the television in order to put it on or off or do something on the television. But these days, we have remote controls. We just sit somewhere in the room and then remotely we can control the television, put it on, off, change channels, and so on. So the idea of remote sensing is in that sense similar to remote control, except that now the difference is that we are sensing instead of controlling. So the remote control controls the system, but remote sensing, we sense, yeah, we are sensing the environment. And why are we so much interested in remote sensing in space technology? Is that most of the things are distant, they are remote. We probably would not get to them, or unless sometimes it costs a lot to actually get to them. So remote sensing is one of our ways, advancements through which we know what is out there without physically being in contact with what is happening there. So remote sensing just helps us to sense things without touching them. That is the core idea behind remote sensing. And when we think of some examples of applications in astronomy, we'll look at how do we know the distances to stars? Yeah, without having been there, no one has ever been to a star, so that we know to some precision or to some accuracy how far away the stars or the sun and other systems are from us. So, for example, I know in the course of this workshop or some other cases, we must have seen like how we get to measure the distance to stars or the sun in particular without being there by method of parallax. So basically, we need to create a baseline of sometimes the Earth, maybe the two points on Earth could form that baseline. And in the case of stars, we allow the Earth to revolve around the sun. So when it goes halfway in that revolution, we create like the longest baseline through which takes about half a year. So we create that long baseline and then we can measure remotely uh, the angle between half that baseline, and through that way, we get to know the distance to stars by method of parallax. If we come down to Earth, if we come down to Earth, we also apply ideas of remote sensing, especially when we are doing finding of geographical traps, that's rock formation deep in the ground. We don't want to dig yet into the ground to make contact. So we use some sounding techniques where we send down waves and receive them back on the surface to do remote sensing. So we send down a wave and it gets back. The time it takes to return is an indication of the distance or the depth, yeah, where we know the speed of the wave. So through that way, we can also measure how far away the rock formation or some rocks or bedrocks are beneath the ground. Okay, so I would like to, in real practical sense, how the process of remote sensing works is summarized in this diagram on the screen. So we have the sun, which is there. The role is to provide illumination or electromagnetic radiation that is needed for some processes. Then the radiation normally has to pass through the atmosphere. There can be interaction. Usually there are interactions with the atmosphere. And then there could be an object, sometimes different from the atmosphere that we're interested in sensing. And so the radiation also interacts with this object. And then in this other way, it's been the radiation is now returning to the satellite or the sensor out there in space. So there can also be emission of or transmission of radiation by this sensor back to the object we're interested in studying. And through that interaction, the sensor picks up or emits or reflects radiation that is reflected on it, or the ones emitted by the surface. And through some analysis, we measure the energy that we can use, and then the other processes are analysis and interpretation using computers, which is where in this age AI comes in. AI comes into play. Okay, so let's start to talk about satellites. So the reason we're talking about satellites is that satellites are vital. They are vital resources for remote sensing. I would want to ask if there's any question at this point before I continue, if something has not been clear before we move on. Okay. In the absence of any question, be mindful, I'm going to be asking mine at some stages. So you better ask if you have any. Okay, so satellites. Why satellites? They are really useful. Satellites are like one of the most important resources we need for remote sensing. And then we're talking about the types of satellites in these slides. One type of satellites are the ones we use for Earth observation and the actual remote sensing satellites. So what they do mainly is to monitor the Earth's surface and sometimes the atmosphere and the oceans. And then the key sensors in such satellites, what they call the payloads, are normally cameras and images that are put on those satellites. And by virtue of where they are in space, they can take images of the Earth or the atmosphere or whatever the interest is for that satellite. Some examples are the Landsat satellites and Sentinel series that are most widely used for Earth observation. And the applications are in environmental monitoring, for agriculture, disaster management, and resource exploration, and also generally mapping the Earth. Like almost all of us have used Google Maps at one stage or the other. So those are products of remote sensing. So the satellites that do these kind of things are classified or called Earth observation and remote sensing satellites. Then we have a second class of satellites that are navigation satellites. Navigation satellites, the purpose are mainly to let us know where we are on Earth for positioning and timing also. So they tell us position, and by knowing our positions, we can navigate. So that's where the term navigation satellites come from. So they help us to navigate by telling us where we are and also the time. They also provide, in addition, time services. And the kind of satellites that do this are like the GPS, which is owned or operated by the United States, and the GLONASS, which is operated by Russia, then Galileo, which is owned by the European Union, and then Beidou, which is the Chinese version of the GNSS. So I would still talk about this because there's a session in the GNSS, and it's going to move further into what we have for the second session. So yeah, I will still talk about it, but just to mention, any kind of satellite system that helps us to position for positioning and navigation and timing, we call them GNSS, which is the short for Global Navigation Satellite Systems. So global navigation satellite systems are the generic names. Then different countries and nations have come up with their versions of the GNSS, which is what is listed here. And then, so when we come to applications, they are mainly for personal navigation, for aviation, like the flights we use for maritime routing, geolocating, and then also even for surveying, precision agriculture, and so on. Then we have the third class of satellites, which are the communication satellites that are mainly for communication. So these are the ones like when we are making phone calls to distant places, the signals sometimes have to be routed through satellites. So these kind of satellites are called communication satellites. And also for television, then when we're listening to television broadcasts, especially the ones like DSTV, uh, Starlink, and also even for internet generally. So anything pertaining communication, the payloads on them are like mainly like transponders that uh, send out communication. Either they receive and rebroadcast to other regions. And next, we have the meteorologists, weather satellites. These are mainly research-based satellites that are put in space to study weather, climate, the atmosphere, and so on. Most of them are also remote sensing satellites. And yeah, they're mainly in geostationary uh, orbits. Those are the ones that provide continuous view of one location. We'll talk about orbits next. I think that's on the next. And then there are the polar orbiting ones that are on the low Earth orbits. Okay. So we have also scientific and astronomical satellites that do other missions other than just weather, which climates that are seen in the previous slide. So these include satellites like the GRACE, the SWAM, the Hubble Space Telescopes, and the rest of them that are put for either astronomy research, space science research, and the rest of them. We also have military satellites that are put specifically for military applications, for national security, surveillance, intelligence, and for secure communications. And also for recently, maybe more recently, the technology demonstration satellites like the CubeSats that are floated everywhere in space these days. So they are like the least expensive, far less expensive to launch, and for that reason, they are normally used for demonstration or for testing. Like if we want to test something before we build the real satellites, they're normally put in form of CubeSats that are very small satellites. So those are the type of satellites, and we want to move into satellite orbits. Any question before we proceed? Okay, so no question. So we proceed. So we talk about satellite orbits now. And broadly, three classes of satellite orbits. We have the low Earth orbits. Those are the ones closest that go in orbit closest to us. Then there are the medium Earth orbits, and then the geostationary or geosynchronous orbits that are farther away from us. So starting to talk about the low Earth orbits, they are just normally about 300, as close as about 300 kilometers, but can extend to up to 2,000 kilometers thereabout. And yeah, they are known to be very fast. Of course, Kepler's law of planetary motion tells us, yeah, that the closest ones are the fastest, usually the fastest. And it takes about 90 minutes, roughly, for this kind of satellites to orbit the Earth. So in just 90 minutes, an hour and 30 minutes, they've completed and they've gone around the Earth. So they go around the Earth several times in a day. And yeah, they are the type that are typically used for Earth observation, and also the International Space Station is also in that class of the low Earth orbit. Then we have the ones in sun synchronous orbits. Yeah, sun synchronous orbits are also they are a special type of the LEOs, the low Earth orbit satellites. And they are special in the sense that they are put in a kind of orbits that help us to return specific uh, illumination of the sun over any given location. So when these satellites pass over any given location on Earth, they always pass that location at the same daytime, at the same time of the day, so that the sunlight illumination is always very similar, and that's why they are called sun-synchronous orbits. They are normally in altitudes of around 600 to 800 kilometers, and like I said, they pass over the same uh, locations at the same local solar times every day. So whenever they pass any location, it's at the same, always at the same sun time. So they are normally good for this reason, for the purpose of Earth observation, because they provide consistent lightning, the same lightning condition for any time they pass and they map the Earth. So that for sun-synchronous satellites, yeah, or orbits, which are a special type of low Earth orbits. So then we have the medium Earth orbits. Yeah, the medium Earth orbits are now a different class from the low Earth orbits. Okay, I thought someone raised their hands. Okay, so yeah, they're different class, and they're in altitudes of around 5,000 to 30,000. And they are slower than the low Earth orbits, of course, for that distance. And the typical use of these satellites are for navigation. We're still going to talk more about them. They are like the GNSS satellites. They are usually put in that kind of orbit that is not too far away and not too close to the Earth, and yeah, for this navigation application. Then we have the geostationary orbits, which are by precise calculation, if we really want to fix the satellites over a given location, which is the meaning of the orbit. So they are orbits in which when you put a satellite, that satellite would always consistently have a footprint at the same Earth location. So it doesn't change, the footprint does not change. So it rotates around the Earth. Yeah, sorry, it revolves around the Earth at the same rate at which the Earth itself is rotating about its axis. So we have always the satellite mapping or looking at the same Earth location every time. And there are special kind of uh, satellites that are used mainly for communication. And the reason they are used for communication is obvious. Like the satellites we point to when we mount our DSTV, the DSTV. So those, if not, then our dishes will need to be doing tracking. We'll need to be tracking the satellites because they move as they move, and maybe other ones come, but that would be a more sophisticated science to have in our homes, especially specifically at this age. So, so those communication satellites are normally routed and meant to just be stationary. And then we just point our satellites to those, our dishes. Our dishes point to those, to the directions where the satellites are. And by virtue of whatever we get, yeah, it's constantly. So the satellites are always, the dishes are always pointing at the satellites, and we don't need to track, the locations don't need to change. So those are geostationary orbits that are around 35,000 kilometers. Like they are about the most distant satellites that orbit the Earth. There are also other ones that are in some kind of orbits around now the sun, or in some kind of motion within locations in space where we call the L1. And so they just fixed in those parts. Is there any question?
Yes, there is, Doc.
Okay. Yeah, I heard the sound. Okay. Yes, was the
Okay.
question is in the comment.
Okay.
Okay.
No,
Can
no.
you please?
Can I ask?
Okay, you're asking. Okay. Yes,
Yeah.
please.
Okay. My name is Musa. Before we move to the next topic, you talked about the geostationary satellites using DSTV as one of the examples. Um,
Yes.
okay. We are not all positioned in the same spot on the Earth. So, my
Yes.
question is, why is it that
Mm.
somebody in South Africa can
Yes.
get DSTV and somebody in Nigeria can also get DSTV, but we are in different positions on the earth? What is their percentage coverage? Because they are
Mm.
synchronized to the motion of the earth. So if you have
Mm.
one, um, it won't be able, in my own estimation, to cover the whole part of the earth.
Yes.
So
Okay. Thank you.
how?
Yeah.
Thank you.
Yeah, thank you for that question. I think it's an interesting thing to think about. Yeah, but the short answer is that there are not only one geostationary satellites, like the DSTV probably has several of them that cover different parts of the globe where they have customers, countries. And also, so what also happens is that when the satellite is there, for example, the same satellite can actually be used by persons or customers in different countries. So there are like no country boundaries to using. So like the DSTV, for example, does not need to launch one satellite for Nigeria and launch another one for Cameroon, Benin Republic, and so on. So there can be one satellite that or so long as it's in on the horizon of those countries and the dish can comfortably be pointed. So and that is also why when you're installing your DSTV, so it's not always so there are little changes on the direction the dish is pointing. So in some locations it points in one direction. If you live in another location, you realize that the direction you need to point it is different because you need to kind of point it towards the satellite. But of course, like you also mentioned, one satellite globally will not be enough because we can't have that. So DSTV, for example, has several satellites around the countries where they do operations and yeah, sometimes even more than one. So because of business growth, so they usually would have backups of these satellites and yeah, the things that they do. So I don't know if that answered your question.
Okay, yes, sir. Yes, because when I was, I do a lot of satellite tracking in the office, especially the
Okay.
polar Earth orbiting satellites. Especially the
Yeah.
weather was NOAA 15, NOAA 18, NOAA 19, and Meteor 2, 3, 2, 4.
Okay.
But
Interesting.
for the
Yeah.
communication satellites, I
Mm.
also understand that they are always launched into a constellation. That
Mm.
means it's like they do like something like handover as the Earth
Mm.
is rotating about its axis. You have satellites
Mm.
launched into orbit into a constellation that covers every part of the globe. So
Yeah.
that wherever you are positioned, you are able to just point in the direction that is maybe
Yes.
directly in your over your horizon where the satellite covering that area. Some have 38% coverage of the earth like that. So they are able to
Mm.
join forces and one can pick their signals. So that was why I asked if that also applies to geostationary Earth orbit satellites.
Okay. Yeah. So for
Okay, sir.
geostationary satellites, they are always stationary. And
Okay.
yeah, it doesn't mean that all communication satellites are also stationary. There are also communication satellites like the ones, if we are making phone calls, for example, we don't always need a fixed satellite. But for television and like DSTV, we need that satellite to be fixed. If not, our dish should be tracking it too. Or
Tracking.
and
Okay.
yeah, yeah. But to avoid that complexity, the satellite
Mm.
normally has to be fixed, and the dish just points to that satellite. Those are the advantages of geostationary satellites
Oh,
for
thank you, sir.
yeah, for such application. Then when you go to like the ones that revolve, especially the navigation satellites. I think they are the ones you spoke about being in a constellation. They can be used different. So whichever one of them comes over the horizon, they do they do the job they are supposed to do. Tracking is not required because they are like broadcasting signals in all directions, and we don't need dishes like our cell phones to receive their signals. So wherever, so long as anyone comes in the horizon, signal from it can be received by our cell phones. I will talk more about that for when we come to navigation satellites.
Thank you, sir.
Yeah, thank you for your questions. So we move to the highly elliptical orbits. Yeah, those are, I think that's the last class I have. Yeah, so there are these kind of satellites that are put such that their altitude varies highly. So sometimes they come close to the Earth. At other points, they move very far away from the Earth, and that's why they are called highly elliptical orbits. So their orbits are not like the other orbits that we've mentioned. They are very highly elliptical, and sometimes they are used for different purposes. For example, in the polar regions, they are used for communication too. They are not geostationary, though. The geostationary orbits are normally around the equator. But if we think of people living in the poles, then they normally use like this kind of highly elliptical orbits for their own communications, which also go and come. But the idea is that by Kepler's law, what happens is that around the poles, they are built to spend a very long time. So the orbits are long. They are far on the pole. So it takes a very long time. They spend very long time over the poles. So as they're moving, spend a long time. And then when they're going down to the equator, they just quickly go and return back on the other side of the pole and spend a long time again. So in those parts of the earth where they are closer, they are fast. They move fast in locations where they are close to the earth. And then when they come over the poles where they are specially designed to spend longer time, then they start like dragging. They become slow. They move very slowly. So you see that they spend a lot of their time over the poles, and like moving over the other parts of the earth is just to be in orbit. And such kind of orbits are called highly elliptical orbits. They were also being applied by the Russians during one of those wars where they were using it to observe a particular location. So they wanted the satellite to spend more time observing uh, certain regions, and then they put those satellites in orbits, in those kind of orbits, so that they spend so much time in in those orbits. So those are the applications where we don't need some kind of even distribution or even time that is spent on yeah around the Earth, but we want the satellite to spend more time in a given location, a given region. Okay. Trying to. Okay. Yeah. So there's a quiz now. I just want to know how many of us have been listening. So I'm asking, the question is on the screen. Which satellite orbit provides the most consistent illumination conditions for Earth observations? Which of the satellite orbits among the ones I mentioned provides the most consistent illumination conditions for Earth observation? And I want everybody to answer. So you drop your answers on the comments, on the chat box. I want to see your answers on the chat box before we proceed. So I'm waiting. Which satellite orbit provides the most consistent illumination conditions for Earth observation? Okay. Yeah, Aman. Okay. Yeah, I have an answer. Don't copy from anyone. Say your own answer. Yes, I know. I understand. Okay, I'm waiting for others. Geosynchronous. Okay. Yes, I have two answers. I'm expecting more than 10 answers. Okay, then the Leo, the mid-Earth orbits. Okay. Those are the ones I said they are normally, when they are passing, they illuminate the same Earth location at the same, under the same lightning condition. The geos, yes, okay. Okay, let me see who has not answered. Okay, Julius, have you answered? Julius, are you there?
Yes, I can. I'm here.
Okay, I've not seen your answer. I'm waiting for you. Okay. Okay, so that is the answer. So they are the ones in the sun synchronous orbits. Sun synchronous orbits. They are the ones I told you are the special type of the low Earth orbit. So those that also answered low Earth orbits are quite correct. But if we wanted to be very specific, they are the ones in the sun synchronous orbits. So the sun synchronous orbits I mentioned earlier, they are in low Earth orbits, but in kind of orbits that they give the sun, the sun is always illuminating the Earth, any part of the Earth, or they pass any part of the Earth at the same local time. So if they pass for example, in Nsukka, if they pass over Nsukka at 8 a.m. today, tomorrow or any other day they pass over Nsukka, they will always pass at 8 a.m. So they don't pass today at 8 a.m., tomorrow at 9, or so you just always know they pass at that same local time. So they are sun synchronous orbits. And so by that property, that means it is the same time, the same sun condition is when they are passing any given Earth location. So that is good. Yeah, I'm glad most or maybe about half got it. So we move on to the next part. Yeah, or something. Does anyone have something to say before we move on? Okay, I forgot to just, okay, yes.
Move on, sir.
Okay, I forgot to mention because I think there can also be a confusion between sun synchronous orbits and geosynchronous orbits. there are different types. There are different types of orbits. They don't mean the same thing too. The the sun synchronous are the ones I've explained. They are in low Earth orbit, so they can orbit the Earth a number of times in a day. But geosynchronous orbits are similar to geostationary orbits. The difference is that the geostationary orbits are spatial orbits. They are the ones specifically around the equator. So the geostationary orbits are a special class of geosynchronous orbits. So they are different. The geosynchronous orbits are rather more similar to geostationary orbits than they are to sun synchronous orbits. They are very different orbits from the sun synchronous orbits. Yeah, so sun synchronous orbits are the answer. And then, so we move on to the GNSS, which is the last part of this session. Okay. So the GNSS, like I said before, it's acronym for the Global Navigation Satellite System, and it is the generic name for any system at all on Earth that depends on satellites to provide us with our positions. Before the GNSS systems, we normally use stuff like compass to know directions and where we are, where we're going to. But with the invention of satellites, when we realized that satellites could help us do better, GNSS systems were now developed. So the GNSS is the generic name. Any satellite system that helps us to know where we are, our positioning, timing, and helps us for navigation. They are called Global Navigation Satellite Systems. And then, so it is of interest to us here because it also provides vital resource for remote sensing applications, as we are going to see in the next, after the break. Okay, so the GNSS, there are a number of them, different countries are coming up to develop their own GNSS system. The first and the foremost GNSS system we know and which most of us use is the GPS. In fact, most people think the GNSS is synonymous with GPS. So when you talk of GPS, sometimes they're actually used interchangeably, talking about GPS and GNSS. The reason being that the GPS was the foremost GNSS system that was built by the United States, and somehow it overshadowed every other GNSS system, and everyone talks about the GPS as if, it is the leading GNSS. And it was put in orbit in 1978. That was very long ago. And then we also have the GLONASS that was almost immediately after the GPS. Yeah, those were kind of battles between the superpowers, the United States and Russia. So Russia put up their own navigation system, which they call GLONASS. Coincidentally, the GLONASS has, if translated in English language, has the same abbreviation as the GNSS, that is the generic name. That is the Global Navigation Satellite System. Then a little more recently, in the last about 25 years ago, the Chinese put up their own system, which is the Beidou. And somehow the Beidou seems to be dominating in terms of numbers, the GNSS systems. But the GPS already has its own has already stamped its dominance, and everyone was already using it. But in these days, when companies design GNSS systems, they normally also include, especially the Beidou and the GLONASS, and then more recently, the European Union came up with theirs, which is the Galileo. That is the fourth one on this slide. So 4 of them, as at now, are the ones that are truly global. Some other countries are developing theirs of Worth mentioning are the Japanese QZSS and the Indians IRNSS systems, which are not yet global. So they are still putting up their systems, their satellites in orbit. I would explain what this means next to say they are not yet global, because to make a global system, you need a minimum number of satellites. So you need a certain number of satellites, not 5, not 10, as we would see. Yeah, so this is a quick summary of the 4 satellite systems that are truly global as at now in terms of their orbital planes and then the minimum number of satellites they require. Okay, so quickly rushing now through like what is a bit scientific or what needs some thoughts here is, how does the GNSS work? How come a satellite, by virtue of satellites being in space, we're able to know our positions on Earth? How does it work? I have my cell phone on there. Then the cell phone has a GNSS receiver that enables it to tell me exactly where I am on Earth. How does it work? What is the principle behind satellites being able to tell us where we are on Earth? So this is how it goes. So each satellite continually sends out information about its own location and time. So each satellite that is out there in space, each GNSS, each satellite that is built for navigation, the only job that satellite does is that it continues beeping out its own location and time. So the location in space, the X1, Y1, Z1, and T1, I'm using as an example. So we have the X, Y, Z coordinate for space and then T for time. So those are the information contained in the radio waves that are being beeped out by this signal. And then what happens is that we want to know the location and the time of any given receiver on Earth. So if I have my cell phone on Earth here, I want to know the location and the time of any particular receiver, like of my own cell phone right now. Let's call the position of my cell phone X, Y, Z, and T. Then we know from our elementary geometry, from coordinate geometry, that the distance between these 2 locations, X, Y, Z, T, and the one of the satellites, X1, Y1, Z1, and T1. So that distance can be calculated in coordinate geometry by this formula, D is equal to that. And then if we use the fact that the speed of the radio signal, which we know is the speed of light, is constant, if we assume it's constant, then we can use this formula to derive that the distance is also equal to the speed multiplied by the time interval when the signal was transmitted by satellite T1 and when it was received by my cell phone on Earth T. So if I do that replacement in the original equation, we'll have this final equation. And then yeah, so we don't know in this particular equation, which is the same one we had in the previous slide. We know X1, Y1, Z1, T1 because the satellite tells us, but we don't know X, Y, Z, and T, which is the location we want actually to know, which is what our receivers, our cell phones should tell us. So I want to ask the question now. It's just a bit elementary maths. How many of these kind of equations do you think we know? If I want to solve for the exact values of X, Y, Z, and T, I want to know the values of X, Y, Z, and T. I know every other thing in that equation, but these 4 parameters I don't know. If I want to know the values of those 4 parameters, how many equations, how many of such equations do you think we need to accurately decide or determine the values of X, Y, Z, and T? Yes. Any clue from elementary maths? Okay, let me put it this way. Is there an answer already? Okay, okay, thank you, Ali Kranz. Yeah, the answer is 4. So because there are 4 unknowns, so we have an equation where we have 4 unknowns. We also need 4 equations to exactly decide that. And this is just basically what the GNSS receivers do. So they receive such information. Yeah, they receive such information, and then they are able to tell us where we are. Okay, thank you, UK. Yeah, 4 is correct. So yeah, and this happens to be the minimum number of satellites we need. We need to receive signals if we want to know our exact locations. So if we are on Earth and we need to know exactly where we are, we need this kind of equation. Then we need another satellite to tell us its own X, Y, Z, and T. So if a second satellite tells us its own X, Y, Z, and T, the third one tells us, and the fourth one tells us, within the algorithm of the receiver, it can compute the values of X, Y, Z, and T. And that is basically what receivers do. That is what the algorithm in receivers are built to do. Okay. So our receivers need at least 4 satellites to be able to compute their locations X, Y, Z, and T. So we now have this set of equations where we know the values of X1, Y1, Z1, X2, Y2, Z2, X3, Y3, Z3, and so on. So we only have 4 unknowns in those set of 4 equations, and we can precisely determine the values of X, Y, Z, and T. So the algorithm on the GNSS solves these equations to obtain that, as I said. And then now, this is where what I mentioned earlier comes in. In order to make sure that every location on Earth receives signal from at least, so in order to make sure that that wherever you are on Earth, you're going to get at least 4 satellites in view, or you're going to be able to receive signals from at least 4 satellites. So we need a total of at least 24 satellites. I'm using the GPS as an illustration, the GPS constellation now as an illustration. So there needs to be a minimum of 24 satellites to have a global coverage so that wherever on Earth you are, you can receive signals from 4 satellites and be able to compute your location. If you receive from three satellites or 2 or less than 4, then you cannot be able to compute where your location. And in GNSS terminology, we normally say that we've not the receiver has not gotten lock, so it will not lock. So the receiver only locks when it gets signals from at least 4 receivers. Sometimes it's a get from more than 4 receivers. And in those cases, then it becomes a problem, an optimization problem, where it tries to solve for the optimal position using sometimes on the GNSS, like the one we have in Isuka presently, you could find that it receives from more than 10 satellites, especially if you now, I mean GPS alone. Sometimes you could receive from close to 10 GPS satellites from that location alone. And then when you add the one from other constellations like the Beidou, GLONASS, then there's so much. So the GNSS has become so large these days that we need more than we require in some sense. And yeah, so the problem becomes so much optimization to say things much more precisely. And yeah, so that is that for the principle of operation. Yeah, so here is a big problem that may appear small, and that is where next we are going to. In those equations, we assumed that the speed of light is constant throughout the intervening medium. But this is not true practically. In practical sense, this is not accurate, is not correct. And why is it not correct? Is because there's a part of the atmosphere which we call the ionosphere that has a substantial amount of ionized particle. And from our elementary electromagnetism, we know that when electromagnetic waves pass through a region of charged particles, they interact with those charged particles in some ways that eventually cause delays of the order of the density of the charged particles in that medium. So that delay makes it that the value of C is not constant in reality. And so the ionosphere, yeah, the ionosphere, the ionosphere causes a delay, which we call the ionospheric delay, and it is the major source of error for the GNSS. It's the major source of problem. So when we see GNSS systems not performing or giving us wrong locations, the ionosphere is one leader that makes these things makes it difficult for us to operate GNSS effectively. So to make matters worse, the ionosphere is even highly variable. So within a day, the variation in the ionosphere is large, and the same variation we don't expect tomorrow and the next. There are variations that are within a day. For example, in the daytime, the ions get more concentrated, and at night, there's reduction. Then there are also seasonal variations. There are also variations over 11 years, solar activity, and so on. And so these things complicate. It doesn't make it easy that we can just quickly or easily correct for. But there's also another way that in space science we normally use to correct the effect of the ionosphere, which is by using dual frequency or multi-frequency receivers. So instead of the satellites transmitting only at one signal, although it's already designed to transmit like the GPS transmits in at least 4 frequencies, but receivers now can have the capability to receive from 1 or 2 or 3 and or 4, depending on the kind of receiver and depending on the permission that is granted to that receiver. And yeah, so that way, when a receiver receives signal from different frequencies, the same satellite, but different frequencies. What happens is that those two frequencies, as they pass through the ionosphere, they are delayed at different rates that have something to do with the frequencies. And because of this, yeah, we're able to estimate how much delay that the ionosphere introduces. I see there's a question here. It says, is it possible for someone to advance Is it possible for someone to advance technology more advanced than satellites like space drones? Sorry, maybe you can ask because I didn't understand it reading. Can you ask Aman Harun?
Then
Yes, please. You
I'm
can ask.
saying
I
that
didn't. Yeah.
I'm saying, is it possible for someone to create a technology more advanced than satellites to maybe replace it or work with that type of technology like space drones or something like that? Like, is it possible for someone to create another model that can replace the satellites or work with the satellites? More likely to
Okay.
replace it. Like
Okay. I
how
think yeah, I get your question somehow now. Yeah, and I would say yes in some way, and maybe by answering it, it means it's just an extension of another class of GNSS receivers. But with yeah, because what I think you would think of now, where you don't, it's maybe where you are sending a signal from Earth. Is that what you're suggesting?
I'm saying, like, to advance a system more advanced than satellites, like a system that could replace satellites, like that will take over. That's what I'm trying to say, like how we used to
Yeah,
use
what kind of systems now?
Like, for example, you said used for governments and thing, like instead of using satellites, they use drones or something like that.
Okay, then there
That's
would
what I
be
mean.
a,
Like we used to use bicycles, now we use motorcycles like that. Yeah, that's what I mean. Evolution.
okay, yeah. So just to be plain enough, I think there's no extent we will go in technology that will say this is the highest we can go. We will say this is the highest we can do. There are always more open rooms for things to be done. But thinking of what can be out there for the purpose of navigation, I think the GNSS is like the most complicated or like the most advanced system we can think of now. Maybe when technologies evolve, we can think of deeper things that I think would still be some kind of satellites. Maybe not in the same configuration of the GNSS we have now, but maybe some things that still uh, transmit or send out, beep out signals, but maybe not necessarily. um, Yeah, not necessarily satellites or in the same configuration of what we call satellites on Earth today. Or what do you think? Does anyone have suggestion or something to add or to
I
answer this question?
so I think what in my own understanding he's trying to point out is the
Yeah.
possibility of having like drones replace satellites. Because for example, currently, if you for
Mm,
surveillance and for defense, you
mm,
deploy drones. So is it
mm.
possible to have drones replace satellites in space?
Okay.
Mhm.
Then, yeah, I think then they would become satellites in some sense, but okay, maybe they are not in orbit. That will make them different. And then what energy is going to keep them flying? Those are some basic questions. So
Yes, yes,
now,
that's the
uh,
questions where
yeah, we'll now have to answer it. If we want to use
yeah.
drones, then we need to think about the energy that keeps them. Yeah, so because we will not need to maybe drop them unless maybe we drop them and fly more drones. And that would be complicated in the sense also that by the way the GNSS works, there are ground stations where the accurate position of each satellite and time is determined and put on the ephemeris. So there's already a lot that makes the satellite system that if we are flying drones, okay, then the drones themselves, first of all, have to decide their positions. By how? That is the next question. Remember the principle through which the GNSS is operating. It's transmit beeping its own position, which is fed to it actually from a ground or control station on Earth. And yeah, through some specialized dynamics, so which monitoring or operating 24 of them globally is already a huge task. And if we think of flying drones, then we are also limiting the altitude. So when we think of the altitude, then that means the number of the coverage of that drone is nothing compared to the coverage of a satellite. Yeah, so only few people will be connected to that drone. They need four of the drones. And so there are some things that may make it, but nothing, like I said, is not possible with advancements in technology. But you think of those kind of minor problems. I call them minor, but they're actually big, where you have to fly the drone and then you have to decide its position. You have to make sure it is. So which way are we going to be deciding its position by? Is it using the GNSS, the satellite one now? Or
Oh, that's clear now.
yeah, yeah. Okay. Any other question? I think this is the last slide actually, and this is just in time.
Thank you,
Yeah,
Professor.
yeah, thank you. So I have my own questions. Yeah, I have my own questions before we go. So the first one is, what is the minimum number of GPS satellites that a receiver needs signal from in order to compute its own location? I think we already answered that. So, okay, good. Yeah, so 4. Yeah, 4 is the answer. No, not 24. 4. Yeah, 24 is the global coverage, but for one receiver, the minimum it needs is 4. For one receiver, but globally, what we need is 24 in order for each one to have 4 also. So the second question is, which factor is the most significantly affects the GNSS accuracy? So I need to see the answers for this one. Which factor most significantly affects good? Okay, I've seen 3. Okay, yeah. Yeah, thank you so much. I think we all got this. It's the ionospheric delay that most significantly affects GNSS accuracy. And then how can we correct for it? This one I need like someone to volunteer to answer by talking. Okay, is it multiple receivers? Okay, dual frequency receivers. Not multiple receivers, but dual frequency, many
Dual
frequency.
frequency receivers.
Yeah, yeah. So if we can have multiple or dual frequency receivers, that's a receiver that can receive signals at many frequencies, at 2 or more frequencies, then it can also estimate what the ionospheric delay is. So that's, yeah. And aside that, we can also use ionospheric models. So we can use models of the ionosphere that estimate for us how the ionosphere would be at any given location at any given point in time and space. So when we know that, then we would also be able to correct, depending on the accuracy of that model, we'd also be able to correct for the error. Yeah, so thank you for listening.
Okay, thank you,
yeah.
Dr. Daniel, for that very interesting lecture. But before we proceed to the break, I think Julius is raising hand. Julius,
Okay.
do you have any question?
Yes, I do.
Okay, please drop your question.
Where is the source of the time that is used on the satellite? I mean, is it Earth time or what is the source?
Okay, so the GPS satellites have their, I forgot the name, but this specialized timing device put as part of the payload. So yeah, that is what, and then there are also the ones on ground that always cross checks. Yeah, so there are ground stations in addition to timing that also checks the location of they are actually tracking the different satellites and knowing their locations and yeah, correcting sometimes. They have thrusters in there that they used to like maybe push them back to certain orbits or locations. But whatever the location is what the GPS satellite is meant or is transmitting at any given time. So there are onboard yeah there are onboard sensors for time calibration. Those are the most accurate timers we know of. I forgot. Those of you in astronomy, I think you know it. Any anyone looking that will help us?
I was
Okay,
thinking
yes,
maybe it's atomic clocks because
yes,
Yes, yes,
exactly.
atomic clocks are used.
Yeah, the atomic clocks. Yeah, the atomic clocks. That's the word I was looking for. So they are put on board the satellites. So their accuracies I learned of the order of nanoseconds. So they are accurate up to the order of nanoseconds.
Thank you.
Yeah.
Okay, thank you so much for that explanation. I don't think there is any other question there. Well, I think Aman dropped a question on the chat. Are there satellites
Okay.
that use advanced AI and quantum chips?
Yeah, of course, we
Do you
would
have it?
expect these
Yes.
days. Yeah. Yeah, would expect these days to have, but most of the processing are done on ground. Most of the processing of information we get from satellites are done on ground, except maybe some few that need to be automated, that the satellites need to do and react to them. There would be, I'm not sure, I don't know of any now.
Okay.
Yeah.
It's okay. Thank you.
Okay. Yeah, thank you.
UK Okoro, I think we can see your comments. Thank you for that appreciation.
Yeah,
And
thank you,
thank you for
UK.
being there for us too.
Thank you,
Okay,
Prof.
I think
Mm.
yeah, I think with this we can go on break for about 30 minutes so that we can allow our lecturer to take water or take tea while we also
Okay,
conclude the
I'm not,
session.
okay, I'm hearing you now. Okay, okay,
I said
thank
we are to
you.
reconvene by 12:45.
Okay,
Yeah, that's just a 30 minutes break, and then we will
okay,
bounce back to complete the exercise. Thank you so much
okay.
for your time and whatever you
Yeah,
have
thank you,
sacrificed to
Prof.
put these things together. Yeah, thank you so
Yeah,
much. So
yeah,
we'll
thank you
sit
so much.
on break. Yeah.
Yeah,
Thank you,
bye-bye.
Prof.
Yeah, thank you. Yeah,
Yeah, so I think you can share your screen and then resume the lecture. Thank you.
okay, thank you. Okay, so this is the second part. Yeah, this is the second part of uh, yeah, the whole thing. So in this part now, in this second part, what I'm going to be doing, only two major things. The first one is to talk about remote sensing application. I just want to confirm, can we hear me? Can everyone hear me and see the screen too?
Yes, I can hear
Yeah.
you.
Yes, very well.
Okay, thank you for the confirmation. Yeah, so the first part of the this other class is going to be on remote sensing applications by GNSS radio occultation. I would explain what that means, and then machine learning and AI applications in remote sensing. Okay, so we'll start with this term, radio occultation, what it means. So occultation generally, when we say there's an occultation, I think astronomers also use this term a lot. We say there's an occultation, it just means like one object passes behind another one. So one object is occulting the other. So that is generally what occultation means. But then in GNSS terminology, when we talk of GNSS radio occultation, what it means is that there is a GNSS satellite that is transmitting signal down to Earth, as we already saw in the previous class, earlier class, and then this signal has to pass through the atmosphere. So the atmosphere now is the one occulting the GNSS signal. It has to pass through the atmosphere. I will explain the procedure in better detail shortly. So it has to pass through and then it gets down through the atmosphere in down to another satellite in the low Earth orbit. So I made this simulation for clear illustration of how the process happened. So this is our Earth floating in space, and we know that around our Earth is the atmosphere, but is the atmosphere, whether ionosphere or the ionosphere is part of it. So there is the atmosphere, and then that is a low orbit satellite down there. Hope we can see. Yeah, so that is a low orbit satellite, and then there's an high orbit satellite. So I just did as a simplified explanation of exactly what is going on when we talk about the occultation. So one thing with this process, or why it is important, is that it is one good application of remote sensing, where we use remote sensing to measure ionospheric parameters, or atmospheric parameters more precisely. So we measure properties of the atmosphere, as we're going to see, by using this technique. So the technique involves normally two systems of satellites, not just two systems. So we already discussed the GNSS satellites that are in medium Earth orbits. The GNSS satellites are in MIOS, middle Earth orbits. That is that one. It's the higher satellites. That one going at a higher orbit. Then there is this other low Earth orbiting satellites going very close to the Earth, actually within the atmosphere normally. So that satellite, the low Earth orbit satellite, is normally within the atmosphere, while the higher one is the GNSS, which we already spoke about. So it is this other low Earth orbiting satellites that now gets the data itself. The GNSS system is not the one that directly gives us the measurement. We get the measurement directly from the low orbiting one. And the way it works is that an occultation will normally start happening when I wish I would stop it. Okay. Yeah. When the two satellites just start seeing each other. Let me see this. Okay. Yeah, I'm trying to move. Yes. Okay. Yeah, so there is that satellite up, the higher one, and there's a lower one. So they don't see each other, for example, right now. Then when this low Earth one starts rising, when it just starts coming up the horizon where it can see the satellite, is where it starts happening. So at that point, you would find out, I also added that, so that's what happened. The red line shows how the GNSS signal, the one we spoke about in the last class, that is being transmitted by that satellite. So it beeps it out, and somehow when it enters the atmosphere, it does not continue traveling straight. So there's some kind of bending or refraction that happens in the atmosphere when that signal enters the atmosphere, and the degree by which it bends is what tells us information about the atmosphere at that point. That's what we call the refractivity of the atmosphere. So yeah, that is a rough picture of how radio occultation works. So there are basically two satellites, one transmitting the signal, that is the GNSS, which is in a higher orbit, and then the one receiving the signal, which is the the satellite we are talking about in the low orbit. There are different missions that have been sent like that. The one peculiar one is the cosmic. There are many of them. The one peculiar one is a cosmic satellite system. It's also in the constellation of about 6 satellites, and each one occultation can happen with each one with any given GNSS receiver. And measurements are taken. So how these measurements are taken, which is the remote sensing part now, is what we are interested in. So the simple idea of GNSS radio occultation is that GNSS satellite sends a radio signal, as I've said. Then the low Earth orbit satellite receives the signal. But before it receives the signal passes through the atmosphere, which includes the ionosphere, the stratosphere, and the troposphere. And then the changes in the signal tell us about the atmosphere. That's remote. That's how we remotely sense and measure the atmosphere. The parameters we measure, as we're going to see, for example, temperature. We measure the temperature of the atmosphere at different altitudes without sending a satellite or a balloon. One way we measure similar temperatures is by balloon experiments, where we send balloons a thermometer is on the onboard the balloon, and as the balloon rises, it keeps measuring the temperature at different altitudes and sending them down to a ground receiver. So that way we can do that, but we'll see that is expensive in itself to send one balloon just to make one experiment, and it's also time consuming. But by this system, we normally get millions of temperature measurements in a day, millions or maybe getting to billions data of atmospheric data within a day. So there's also global coverage, like in Africa where we lack equipment. This remote sensing system normally helps us to have ample or good amount of data. So the parameters, we measure, and why that bending happens, why there's a change in the signal, is because the atmosphere has density. There's air density, it has temperature, it contains water vapor and also free electrons, like we spoke in the ionosphere last time. So these properties cause the signal to bend or refract or to be delayed within the atmosphere. And through that way, the atmosphere is being remotely sensed. So we can do some measurements about the atmosphere. So from the signal, we can derive the main parameter we derive from this signal is the refractivity of the atmosphere. And then from the refractivity, using a set of systems I'm going to explain next, we can get the temperature, the pressure, the atmospheric density, and even the electron density. That's the density of charged particles in the ionosphere. So it can be measured through this remote sensing way, which is different from the way we do physical measurements or in situ measurements of the same parameters. So how do we get refractivity? Starting from the bending angle. The bending angle is, I should have done this illustration here. So looking at this simulation again, if the signal had continued straight without being bent, so the angle it makes with the straight line that would have continued versus the one that has bent. So that angle there, by how much the signal has bent, is what we measure as the bending angle. So if we call it eta n like that, then we define the refractivity based on the bending angle as this formula. So we can, from the bending angle, we can get the refractivity using this formula. So that's the first step. We get the refractivity from the bending angle. And then in the neutral atmosphere, that's below 60 kilometers. If that happens at that point, we have this equation that is well known and well used by researchers or scientists in the lower atmospheric sector. So in this formula, N is the refractivity, which we already measured from the previous slide. Then P is the pressure, T is temperature, and E is the water vapor pressure. So we see that refractivity depends on those three factors. So how then do we go about measuring each one just from the same refractivity formula? So the first one is this basic physics, this gas law that tells us that the atmospheric density is related to pressure and temperature by this. So once we know P over T, we immediately can get rho, the atmospheric density. So we can measure the atmospheric density if we know P over T. Then the next question is, how do we get P over T? R is a constant. So to get P over T, so there's this also approximation from the formula I showed earlier, which is what happens above 800 kilometers. This is precisely when we exclude, I'm going back to it. Yeah, so when we exclude this water vapor part of the atmosphere, which is exactly what we get in the above about 8 kilometers, the water vapor pressure goes to zero. So if you approximate it to zero, then we are left with the fact that the refractivity only depends on pressure and temperature at those altitudes. So back to there. So with this way, we have an expression for P over T in terms of the refractivity, which we already know. And then there's also the hydrostatic balance equation, which is this. And then, remember for the dry atmosphere, which is about 8 kilometers, we have this, and then for the wet atmosphere, we have this. So this hydrostatic balance equation tells us the rate at which the pressure changes with altitude. So starting from a reference point, which is, for example, Z, at a particular height, normally, let's say 60 kilometers, at that height, the pressure is very minimal, it's very little and can be estimated or roughly approximated. So starting from a rough approximation at that altitude, we can compute the pressure, how the pressure changes with Z as a function of rho and G, which are constants that we have known now. And so if we do that, that means at any point in time, at any altitude where we know the pressure, we can use this formula to derive the temperature. That's for the dry atmosphere. But for the wet atmosphere, we can do the same, except that we need additional information about the wet vapor, that's the wet part of the atmosphere. And for GNSS frequencies, this is for ionospheric density. So this is how we do it. I was just going to mention that, here we're separating the temperature and the pressure. How we do it normally being done to estimate the water pressure is normally from models or from other lower atmosphere measurements, the water pressure normally estimated from there, and then we can derive the pressure, the temperature, refractivity, and more appropriately estimate the humidity. So if we go to the ionospheric density, it's basically similar principle. So we still measure the bending angle, and then from the bending angle, we get the refractivity. Sorry, rather the refractive index. Yeah, which is a product of which we can also get from the bending angle. And then, using this equation, we know, for example, the frequency of the GNSS signal. And then, we can estimate NE, which is the electron density. So that is the way, the principle and the way we normally measure these 4 parameters from ionospheric electron density. Any question at this point before I ask mine? Okay, I see there's a question from Aman. I think you are asking how the system measures water pressure, the water pressure.
How does water vapor get pressure? Or
How does what?
how does water
Yeah.
vapor exert pressure exactly?
Oh, okay. Yeah, because the moisture content, and normally also has to do with temperature. So when the moisture particles are higher, even with the pressure that is due to the dry component, the pressure of the dry component, which is the pressure of the amount of gases above it. So that pressure builds, uh, adds to the water vapor itself. So the water vapor itself has pressure because each particle in the system also has temperature. They have temperature above 0 Kelvin. So since the temperatures are above 0 Kelvin, they have kinetic energy and therefore exert their own pressure. So the reason it is being distinguished from the dry component is that because of the property of water that is not like a dry gas, not like the other gases that make up the atmosphere.
Why do you measure the electron density only for the ionosphere? Why not the exosphere or the mesosphere?
Okay, the mesosphere and the exosphere are actually parts of the ionosphere. So they are not like different. So when we talk of the ionosphere, we're talking of a region of the atmosphere that is ionized. So it's not a category of the atmosphere when we think of the atmosphere as being made up of those four layers. The closest to us is the troposphere. Above the troposphere, we get the stratosphere. And then above the stratosphere, we have the mesosphere, the exosphere, and so on. So the ionosphere begins somewhere between maybe the upper stratosphere, sometimes in the upper stratosphere. So the mesosphere is usually a part of the ionosphere. The exosphere is also a part of the ionosphere. So the ionosphere extends starting from wherever we start getting charged particles, of which the mesosphere is part.
What about the electron density of the stratosphere and troposphere? Why don't you measure those ones?
Yeah, there are no electrons normally in the troposphere and the lower stratosphere. So the ionosphere usually starts at an altitude of around 50 kilometers. And at that altitude of 50 kilometers, we start having maybe part of the stratosphere, the upper part of the stratosphere, and then the mesosphere, the thermosphere, yeah, mainly the thermosphere and the rest of it.
Okay, for
So
gauging from what you're saying, is this correct? You're saying that a wetter atmosphere exerts more
yes,
pressure than a dry atmosphere.
sorry, say
That's
it
what you're
again.
implying. Pardon?
Say what you said again. I didn't
I'm
hear you
saying that
clearly.
doesn't that mean, since you say water vapor creates pressure, that means a wet atmosphere has more pressure than a dry atmosphere.
Exactly.
Okay.
Yes. Yeah, exactly. Yeah, so a wet,
Thank
yeah, and that is why the troposphere in particular normally has more pressure because of the water vapor it also contains.
thank you.
Yeah, so then above the troposphere, it's mainly the dry air or the dry atmosphere. And then when we get to some higher altitudes again, we now start getting ionized particles. That's now the ionosphere.
Thank you, Professor.
Okay, you're welcome. Yeah, so I start with my questions? If there are no other ones, does any other person have a question? Okay, so I asked mine, which I would also want you to type on the chat box. So in GNSS radio occultation, which quantity is directly observed to retrieve atmospheric profiles? What is that property that is observed from which we now get other atmospheric properties? Okay, yeah, I've gotten one answer. Okay, okay, Musa, you're just joining, no problem. The bending angle, okay. Okay, so I think we are right. The bending angle and the signal delay actually, but mostly the bending angle. Yeah, so that is the quantity from which, from that bending angle, we're now able to measure the other parameters. And then which atmospheric parameters can be derived from GNSS radio occultation? Yeah, you can just mention on the chat boxes, I would say, just to know you are following. So which properties can we derive? Which atmospheric properties can be measured by this remote sensing procedure? Okay. Yeah, any of them, not only one. I think we listed around five atmospheric properties, parameters that can be measured. Yes, refractivity is correct. I need more. Okay. Water pressure, temperature, pressure. Yes, pressure. Yes, more. There's one that has not been mentioned. Yes. One more needs to be mentioned, then we continue. There's a parameter that needs to be mentioned. That one is measured in the ionosphere. Okay, electron density, correct, or Ne, as Ali Creans said. Yeah, the atmospheric density is the neutral atmosphere, but the electron density is the ionized atmosphere, is the ionosphere. Yeah, but also the atmospheric density is also measured from from the signal bending. Yeah, so that means we are following, and I'm happy about that. Yeah, so the parameters, yeah, we have refractivity, temperature, pressure, humidity, and ionospheric electron density. Okay, so we move on to the next and the final part of the course, which has to do with AI and machine learning applications. Okay, so this is quite, would I say new or modern? But in actual sense, AI is not a new topic. AI is, in fact, one of the oldest topics in maths. It's been there for ages. People have explained that the only reason we've not been making use of it is because we've not had data. So it's only because we started having data in this data age. So we've come into a system, the age where we started having data, and it's like it resurrected the power of the AI. So we have data to test on AI, but so AI or machine learning is kind of a big data science. Like it's something that requires big data. In the absence of data, AI is as good as non-existent. And that is why over the years, it has been there for decades and no one had been, very little was being mentioned or developed about AI. But compared to the last decade, yeah, maybe the last decade, 2 decades, there's a lot more impact that, or more focus, a lot more focus is being brought to AI because we are in a data age. And just like I explained, and this data age comes with effects. Say comment, let me check what. Okay, which year did AI math start since you said it is old? Okay, I'm not very sure which year. I can't remember for sure, but I know it goes far back, not even the 19th century, maybe the 18th century or even more earlier than that. I can't remember for sure, but something as old as that is really old. Okay, so and I was explaining now why we started having, yeah, why we started having interest in the AI is because of the data we are growing. I explained to you, for example, this remote sensing applications or measurements where we measure the atmosphere. So the data alone, this system, this satellite alone, this cosmic satellite I mentioned about, the data alone it's generating. It's too much, has become too much to deal with an AI, especially with our normal computers. So I work particularly in this field a lot, and a lot of times I normally need to use supercomputers because the data, no matter how powerful my computer is, it normally would not process that. And believe me, I have one of the most powerful computers a normal person can have, but that's still, yeah, that still does not, yeah, when by the time we generate this, even the magnitude of the data, sometimes loading them at once, it's a big challenge for a single computer. So these are the things put together that when you have this kind of data, it becomes more difficult to do science the way it's been done over the years because there's so much data out there that as you are trying to analyze, as you are trying to, the download rate is less than the upload rate. So as you are downloading the data you want to process, more volume of data than the one you are downloading is being put on the platform. So the only rescue is to be downloading them at the same time as using AI to process them. So, and that is why AI applications are important for remote sensing because remote sensing generates lots of data. Okay, so before I dive into explaining details or giving details or specifics about what is being done and how this data is being processed, I find it important to distinguish these terminologies in AI that are normally often confused with each other. So AI itself is the bigger circle. So any system where humans are not thinking about the data, computers are used to think about the data and act or respond or deduce the information automatically by themselves by learning. It's the AI world. Then under the AI world, we have the we have machine learning, which is the bigger circle again. So the machine learning is a subset AI, and it specifically has to do with where the computer is being used to learn things, systems by itself. It's different again from neural networks, which is a smaller subset under machine learning, where we specifically design systems that to model the human brain. And then there's the deep learning component, which is also a part of the neural networks, but with more what we call hidden layers, which I will talk about in the next slides. So yeah, it's like a more complex brain. So when you're building a system with more complex brain, deeper pattern, then yeah, we talk of deep learning. Then the deep learning is part of neural networks, and neural networks are part of machine learning. Machine learning are part of AI. Then when we come to the types of learning, so there are the supervised learning, there are unsupervised learning, and then the reinforcement learning. As the name suggests, supervised learning is a system where we supervise the learning. Exactly in another language, we tell the computer what things are. So we normally say we label the targets. The system is supposed to learn something, but we help it learn it by labeling, telling it that this is this. I will do more explanation in the next slide. And then it's opposed to unsupervised learning, where we don't tell it anything. We just present it with the data and leave it to learn whatever it can learn from it. So that's unsupervised learning. And then there's a completely different set, which is reinforced learning, where we have the system to automatically learn additionally to whatever it has known before. So coming to supervised learning, it's normally applied depending on the problem we want to solve. So when we have a regression problem or classification problem, we can use supervised learning. But when we have clustering or dimensionality reduction problem, we can use unsupervised learning. To explain a little bit more, when we say we have a regression problem is, for example, when we want to build a system that will predict what the temperature is tomorrow. So if we want to predict the temperature tomorrow, for example, then it's a regression problem because we need a particular value. We need the system to tell us, will the temperature tomorrow be 20 degrees Celsius? Will it be 21? So when the model is supposed to predict particular values, yeah, it's regression, especially those values are continuous in nature. But when the opposite somehow is a classification problem, where we need a system to be able to classify inputs, like to tell us that whether there is a dog or a cat or something in the picture. Those kind of problems are like, we want it to classify to say this is an animal, or it's an orange, or it's a this. So those kind of problems are classification problems. The classes are discrete. That's how they are different from regression problems, where the classes are continuous. Then when we come to unsupervised learning, the much the computer can do with unsupervised learning is clustering or dimensionality reduction. Clustering in the sense that we can supply data and the computer will be able to automatically identify clusters within that data. This particular application is used a lot in astronomy, where people like identify clusters of different objects that have similar properties. So when fed into the system, it automatically identifies those clusters. And then dimensionality reductions, when we want to reduce the dimensions of data, it's also a part of unsupervised. So I would explain precisely the supervised against the unsupervised one. So in the supervised learning, we usually have what I call the labeled data set. So you, for example, you show the computer an image and you tell it that this is an apple, this one is an orange, this is still an orange, this is another apple, this is still an... So you give the computer just different samples of what you want it to learn. You show it how oranges look, how apples look, and you tell it this is an orange, you tell it exactly what each one is. So when you have that labeled data set, you now train. You now proceed to training. Okay, I see there's a comment. Let me see. Okay, what is reinforcement thinking or reinforced thinking? Okay, so just as the name implies, you're in reinforcement learning or thinking, training, you are training the system, you are reinforcing certain attributes. So there's usually already a base, there's usually already an existing familiarity of the machine with what it knows, but you want it to know it better, or for example, in real time. So you are bringing the data almost as the data is being measured. You are throwing it into the system and it is using it. So it actually can be a form of supervised or unsupervised learning. But what distinguishes it from the other two is that it's automated and like improving, it's used to improve what already exists. So that's what reinforcement learning or thinking or training is about. Did I answer your question, Eman?
You kind of did, but you're saying that reinforcement thinking is like a subset under supervised thinking.
Yeah, it's not exactly a subset. Yeah, or no, it can be supervised, it can be unsupervised. But what makes it different from that two sets is that it's by itself, yeah, some kind of learning. Just is a class of learning where the system is reinforced. I don't know what better, but yeah, the system is kind of reinforced. More data is continually added. Unlike when we talk of supervised or unsupervised learning alone, we're referring to normally learning that is maybe one time off. That training has been done and it's been achieved. So just to distinguish this pattern, this reinforced learning is especially used in modern times. So where the system is continually updated. Yeah, so that's the class that is reinforced. So it could be supervised, it could also be unsupervised.
So it's a bit of everything, but it's its own thing as well.
Exactly.
So
Yeah.
you're saying what makes it unique is that you can continue to add data unlike the other two.
Exactly. Yeah. Yes. So even when
So
you're
it's like
supervised,
unlimited data. That's what you're saying.
exactly, exactly. Unlimited
While
or
the other two are
continuous.
limited, right?
Yeah, yeah. In this sense of classification, yes, the other two are limited. But with the understanding you have now, you can see that yeah, we can expand. We can make even supervised learning, for example, to become reinforced, and then unsupervised to also become reinforced. So, but in the notion of the classification we have, we can just think supervised, okay, we are supervising the learning. Unsupervised, we are not supervising the learning. And reinforced, we are reinforcing either supervised or unsupervised learning. Is that clear?
Yes, thank you, Professor.
Okay, welcome. Okay, yeah. So another question says, what type of learning is used for robots? So robots can use any combination of learning, yeah, depending on what that robot is supposed to do. So robots, the task of robots are numerous, are different. There are robots that their task are, for example, to predict the temperature instantaneously. So there are robots that whatever, depending on the role of that robot, the job includes to predict the temperature. So you would see that, yeah, yeah, for that robot, what it also has to do supervised, some kind of supervised learning. And then, yeah, I know this idea normally confuses people. People normally confuse supervised and unsupervised. They think they confuse supervised with automation. Supervised actually also means automation. It doesn't mean that when you say something is supervised, it's no longer machine learning or AI. It's still AI. The system also does things automatically by itself. So the system learns by itself and does things. And why we say so is, for example, in this illustration I'm giving, this is supervised. Okay, let me close this box then. So for example, this is supervised. What you're only giving is some samples. But at the end of the learning, when you finish training this system and you give it any other image that it has not seen before, it's able to classify it. So that image doesn't need to be part of the ones you have used to train it. You bring a completely different image that it has never seen before. It's able to tell you automatically that this is an apple or it's an orange. So either system is just based on the problem you want to address. So, but in fact, most of the systems we use, in most cases, a lot of our AI machine learning applications are usually supervised. Yeah, because they give the best results, and they are the ones that make most use of data as much as they can. Let me complete this. Maybe it will become clearer. So when we label this data set, we show it the training, and then the training happens. So yeah, as the training happens, a model is developed. So the model has learned from the patterns you have shown it, and it is now waiting for you to supply new data to it. So you can see that this new data doesn't look in any way like the ones that you have labeled for it. So once you give it new data, once you input new data into the model, it automatically is able to tell you that this one is an apple and this one is an orange. So it's machine learning in that sense because it learns the samples by itself, and it's able to automatically say classify whatever it is being given by itself. So that is how supervised learning works. So back to that question, most AI applications are actually supervised learning that are being used these days. There are also a large, vast number that are unsupervised, as I'm going to show you. So where we normally think of unsupervised learning is in this kind of scenario where we don't label the data set. So we just supply a bunch of samples. Some of them are apples, some of them are bananas, some of them are oranges. Yeah, whatever they are, and then we just throw it into the system. The system is not able, this system is not meant to predict whether this is an apple. It doesn't know whether it's an apple or orange. It doesn't tell you what it is. But what it is able to do is to identify that this sample looks similar to this one and this one. And it's automatically being able to group them according to the classes that it sees. So unsupervised learning for this kind of classification problem is usually used when we have data and we need that data to be classified. So it's a classification problem, not a predictive, it's prediction when you think of classification as prediction, but not like it is telling you like the temperature. If you need to predict the temperature tomorrow, you need to supervise. If you also need it to tell you exactly that this is an apple or an orange or what, you also need to use supervised learning. So unsupervised learning comes where you want it to classify or categorize the samples for you as shown in this slide. So the problem to solve depends on which technique to use to solve that problem. Okay. Yeah, so coming to remote sensing now. So those were preamble, machine learning and AI. So coming to remote sensing, what we normally use AI for are normally land use or land cover classification. This is the case, for example, in satellite imaging, where satellites have gathered a lot of Earth images. And we now can use AI to automatically say, once there's a new image, we're able to automatically identify that this image is a vegetation. So this image is coming from this kind, even the particular class of vegetation it is. And to some more deeper extent, it can tell you what kind of trees are contained in that image. So this is just an aerial view, like images from satellites. These days, they're able to tell you automatically that this is a kind of, just by taking images alone, the AI is normally used to say this is the kind of vegetation you find in this picture. This is the kind of area. It can break down a lot of properties about the area. And also it can tell you that this is a civilization. Yeah, this is where humans live, even estimate the population of people living in the density of people living in a particular image. So those are now applications of AI, what it's being used. And so it's also being used to plan cities, for example, and so on. So that's land use cover. Then there's the cloud detection. So the AI can automatically detect that there's a cloud in this image. One of our recent research was similar based on this. So we had to we collected a lot of images from in Abuja using an all-sky imager. And we used AI to train, and the AI is able to say that this image is cloudy. It contains a signature we call plasma bubbles or not. So that is what it can do. You can use it to classify images to show what kind of features are contained in that image. Then there's the flood and drought monitoring. Yeah, you can also use AI to monitor what is happening in a picture, whether there's going to become a flood, especially when you collect images over time. You can see progression, the AI can see progression in that images and be able to say that this area is becoming prone to flooding, drought, yeah, to drought. And then there's also climate and weather prediction, which I also work a lot to, for example, forecast what the temperature would be at a particular time in the future, or how the temperature is going to change over the future. So those are the kind of things that AI also does. And so then coming to the question of neural networks. Yeah, so like I said before, a neural network is a machine learning model. So it's a subset of machine learning that is specifically inspired by the human brain. So it behaves the way the human brain behaves. In that sense, I picked a notion from one of my former PhD students that tried to explain neural networks in this way. She said it's like a baby. In those days when we used lanterns, lamps filled with kerosene, so the real burning ones. So as a mother, you would want your child or baby not to go close to that lantern. So you will always say, no, don't go close, don't go. But the more you talk, sometimes it's not clear. But until one day when you are not watching and he or she eventually goes and touches the fire, maybe gets hot and would immediately learn by herself that no, next time I shouldn't touch this. So that is the way machine learning are built. The same way human brain learns, yeah, is the idea behind neural networks, and that's why the name is neural, following the human brain. So they normally they're made up of an input layer, hidden layer, and then an output layer. So these are the three basic layers you would find in a given neural network system. So through the input layer is where the data comes in, as the name suggests. So you need to feed in data, and that data is fed in through the input layer. Then from the input layer, the data is transferred to the hidden layer where the learning actually takes place. So the hidden layer is where most of the learning, actually all the learning takes place. And then the output layer is where the final prediction from the learning is brought out. So on the right-hand side, I'm making an illustration. Those lines are kind of weights, which I'm going to talk about, that connect inputs to form the hidden layer and connect sometimes one hidden layer to another hidden layer. We can have so many hidden layers. And when we have many hidden layers, we now call it deep learning. So it's a deep neural network or deep. That's why deep learning is a subset. So, but all of them are neural networks. Sometimes we can just have one hidden layer. It's also sufficient for a neural network, but the deeper it is like building more complexity for the system. And then there's also the output layer. So each layer has neurons. Yeah, each layer contains neurons. Those are the circles now. So the input layer has, like in this particular illustration on the diagram, the input layer has 4 neurons. Then this hidden layer has 5 neurons. The other hidden layer again has 5 neurons, and then the output layer has 4 neurons. So yeah, the input neurons are the ones that receive the inputs from what you've said, and then they pass the results. They multiply the inputs and then they pass to the input layer. So they multiply the inputs by factors we call weights. I'm going to explain that also in the next class. So those are what these lines show. So there are certain weights that each input is being multiplied with. And that's why you see each line from the input connects all the neurons in the hidden layer. So those kind of connections happen and they keep. So a lot of multiplications of certain numbers, which are originally the inputs, keep happening until they come out as output through some refinement. So they multiply the weights and then they pass the results through another we call an activation function, which is one important vital component in neural networks. So what is an activation function, or what do activation functions do, or what do they mean? Yeah. So activation function mainly introduce non-linearity into the network. That's what makes neural network special. That ability to treat non-linear systems. Yeah. And it is the role of the activation function to do that. And yeah, so it's important because in the real world, as we already know as scientists, most of our dealings, most of the systems we deal with are not linear in nature, naturally. So without activation functions, neural network will be very weak and would not be needed as much as we need them today. So that ability to deal with non-linear and complex systems is what makes neural network special and is being brought in by the activation function. So let's see what the activation function is also from this slide. So a lot of time people talk about machine learning and they just say, oh, it's a black box. We don't care or we don't know what happens inside. But that is also not very true because especially these days, we care and we actually know a lot of what is happening inside, only that we don't control what is happening. But at least we know the science or the maths that is going on behind the scene. So as this equation is showing, this is how neural networks work. If you watch these two equations, in fact, I normally simplify it in this pattern. If you watch it, you'll see that it's similar to the equation of a straight line, which we did in elementary school, that y is equal to mx plus c, where we are dealing with the relationship between y and x. So in neural networks terminology, y is the output and x is the input. Then m in geometry, we say is a slope, but in neural networks, we call them the weights, the weight matrices. So that is what this IWM is a weight matrix. And then C, we call it the bias. In this thing, we call them slope, we call it the slope in geometry, whatever it is, but in neural network terminology, they are called the bias. So in neural network, we have the weight matrices and the biases for each neural network equation. So neural networks mainly constitute this kind of linear equation where the inputs, in this case, the input is HM. Sorry, the output is HM. The output from the system is HM, and then the input is IM, the input matrix. Here, I'm using HM, we're using HM to denote the fact that we're getting what happens now at the hidden layer. So this equation is the equation that transmits the input matrix into the hidden matrix. So it's like what happens in the diagram I showed earlier. Yeah, in this system, we are moving from the inputs into the hidden layer. So it is this equation, yeah, that does that job. And by the time now, this tan H is now the activation function I spoke about. So the tan H is a nonlinear function that acts on this linear function, thereby helping the system to learn whatever non-linearity that will be associated with the system. The second equation is basically the same, except now that we are now moving from we are now getting the output. So OM is now the output matrix, and it depends on this input, this hidden matrix here now. So it becomes the input. The hidden matrix becomes the input when the output is now going to be gotten, and it's also again multiplied by the weight matrix in that layer. And then there's also the bias vector. So like the slope and the intercept in that equation. And sometimes it's not in every layer that we must need an activation function. If we don't include an activation function, then it's just a linear system for that. It's better. And there are also many activation functions. There are sigmoid functions. This particular activation function is called the hyperbolic tangent function. That's the tan H, which we know in maths. There are also logistic regression functions. There are all types of activation functions that introduce non-linearity into the system. And I have an important conclusion here that a neural network with enough neurons, there's linear functions with non-linear activations, we can use it to approximate any kind of function to any accuracy we desired. And this is the building idea for neural networks, and that's why this equation says it all. We can use linear system when acted on a non-linear function to approximate any kind of real or non-linear complex system that we may want to be dealing with. It's like there's another question or comment. Let me see. Okay, yeah. So the question says, what is weight and weight matrix? What does linear and non-linear mean? Okay, there are two questions. Let me start with weight matrix. Okay, so like I showed in the first slide, each particular input is going to be multiplied by a certain number, and that number is called a weight. Yeah, so that is what a weight is in machine learning. These numbers are normally randomly assigned initially. So in real neural network process, is a random assignment of the value. It starts with a random assignment of the value, and then those weights are purified or refined. So they are changed. The procedure changes the weights. So the weights keep changing until the problem is optimized. And then that's what gives a good output in something that I may not be able to deal with all through in this short class. It's a bigger problem, and I know I'm not surprised that there's much interest in it because it's always something to talk about, but I will try to say as much, explain as much as I can. But that's the progression. There's usually a random initialization of the weights. So they are initially randomized, and then they are used, and then the process, they keep getting refined until they produce the best or optimized outputs. So one of them is called a weight, but they are normally, in real life problems, they are normally not one. They are normally many. So they are normally a matrix. So there are many of the numbers that form, so there are many weights that form a matrix, and that's why we call them a weight matrix. So when you put the weights together, so they are normally a matrix. And yeah, that's weight matrix. Then what does linear and non-linear mean? Yeah, linear just means we are dealing with a straight line equation like this, which, yeah, like what yeah, like this illustration here. This is a straight line equation where the output is usually the input multiplied by a factor and then with some bias. So that's the intercept plus or minus a constant. That's what a linear equation approximates to. So this is a linear equation. Then when we say nonlinear equations, we are now looking at equations that are able to deal with a lot of complexities that don't just go by multiplying, the inputs by a weight and adding a bias. So there's a more complex, like if, for example, the prediction of temperature, for example, is not a nonlinear problem, especially when you think of the fact that temperature changes within a day. The temperature is changing tomorrow. The temperature tomorrow is not going to be today. And so there are a number of factors that are already affecting, and the way they are affecting it are not linear sometimes. So that's what brings a sense of non-linear systems, and coupled with the couplings that comes with the different inputs. Each input affects the same parameter by a certain weight. Yeah, so it brings, that's what introduces non-linearity.
But you said earlier that real life problems are non-linear. What do you mean by that?
Okay, yes, like the example I gave, to be able to predict the temperature tomorrow, for example, it is not a linear problem. It is not, it is not a problem where we just multiply a constant by the inputs. Yeah, it's not as simple as that. It's a more complex problem that this maybe something is going to be squared, or maybe the input itself is going to be squared or exponent. Maybe we need to take we involve some trigonometric functions, maybe log functions. So yes, once factors like maybe squaring, like polynomials, we have to square the inputs, maybe make it to power 3 or power 4 or even power half, power minus something. So it's no longer just that we are multiplying the input by a factor and adding another constant to it. So it becomes that something has to be done to the input itself before even thinking it's going to be multiplied by another factor and then added.
So
So
you're saying that it would appear as a parabola if we graphed it.
Sorry, say again.
It would appear as a parabola if we graphed it.
The parabola?
For the non-linear, because you said linear would appear as a line on a graph. So non-linear would be like a parabola.
Oh, yes, in that sense, it's just, okay, let's say a curve. Yeah.
Yes.
A curve, yeah. Non-linear it would be like a curve.
Okay. Thank you, Professor.
Yeah, welcome. Okay, so using in real practice, like a recent work we did for atmospheric 3D temperature modeling. So using it as an example of how neural networks work or how they can be applied. So in this particular problem, we are training the system to understand how temperature changes in 3D. That means we're also looking at the changes in temperature with altitude. So we're not only looking at the surface temperature, but we're looking at temperature at different altitudes covering the troposphere and the stratosphere. So we needed to gather information about time each data was obtained. So we needed to feed in that data like that into the neural network. So basically we are showing, this is a supervised learning system where we are showing the system wanting to learn how temperature changes over time. So we have to tell it the year in which that data was acquired. We have to tell it the day of the year. The day of the year is relevant so that it knows the season. I think it helps the neural network to learn the seasonal variations. So because the day of the year runs from 1 to 360 something. So over 1 to 360 something relates to the seasons of the year. Then we also tell it the hour of each day. So it sees whether this temperature was measured at noon or in the evening. So we tell it precisely at the hour as a fraction. So the hour can be 5.235, meaning somewhere around 5 a.m. in universal time. And then, so those are the three inputs we are using for time. And then for space, we're using the longitude, the latitude, and the altitude for that temperature measurement. So we supply that, and then we tell it that this was the temperature value. And we do the same thing. We give a second set of samples, a second set of temperature, telling it the year, the day of the year, all the inputs that correspond to that. And we do this for millions or billions of times. And then, yeah, so we have maybe n samples, where n, normally, I think in the actual work we did, n was several billions of data for a temperature model. And then the temperature is able to learn the connection between each of these inputs. So it sees, this is the non-linearity now. It sees how each of these inputs affects the temperature. So this altitude, I forgot to change it from the slide, my previous slide. I was illustrating another modeling system. But here it's altitude. So we'll be able to predict the temperature for that system by learning. So when it learns, what the learning makes is that the system now has an optimized weight matrix. So there are optimized weight matrices the system has learned, and that is what the final model uses, which is stored as that mathematical equation I showed earlier. So testing is usually done using prior set aside data. So we normally set aside about 15 or 20% of the data, which we use to test whatever the network has learned to see how good or bad it is. And what basically happens in testing is that this is hidden data that is hidden from the network. It doesn't see it. So we presume this data has not been collected. So now that it has finished learning, let's ask it. We know the actual temperature, but we don't tell the network. So we ask it, we tell it, all we do is to tell it the year, the day of the year, and these 6 inputs. So just giving it the inputs alone, it will predict a temperature. From that model. So it will predict a temperature. And we have to compare this predicted temperature with the actual temperature to see how good or bad it is. And like I said, this is not a one-time, it's not a single data. Itself can be millions of data. The data for testing itself can be millions or billions of data also. So we have to test many samples. So we test another sample, and so on. And we can, normally for each sample, we can predict the error for each sample. And to make some averaging of the samples, we can do the mean error. The mean of the errors is one set of averaging. Sometimes we do the mean squared error, or sometimes the root mean squared error, or this other set of parameters. So they are just statistics that are normally computed to see the performance. How good is the prediction? For example, is it sometimes the typical difference between what is predicted and what is actual may be about 1 degree Celsius. So we say, okay, 1 degree Celsius, is it good? Is it okay? Do we want to improve it? Can try to do what we call hyperparameter tuning to change some things and see if the prediction gets better. So more often it's also an optimization problem where we want to see that the responses it's given to the test data is being optimized. It looks like there's another question. Okay, which activation function was used in the 3D temperature prediction? We used the hyperbolic tangent function as the activation function for our 3D temperature prediction. Okay, can the predicted be higher than the actual? Yes, sometimes the predicted value is higher than the actual. Though if it's higher by a large amount, then the prediction is not good. So in fact, a good prediction when we are testing, we normally want to see that the errors are Gaussianly distributed. So there's an equal distribution of higher and lower predictions. Yeah, there's some, maybe not exactly, but at least when you see the error distribution, you see that there are as much higher as much lower errors. That's when you know that the neural network is doing well. But if you continually predict either lower set or higher set, then that means the prediction is not good. Yeah, if there's a bias in one way, then the prediction is not good. So a good prediction should normally be Gaussianly distributed. You have some sort of equal distribution of higher predictions and lower predictions. And then the value of the error is also important. Like when we calculate the root mean squared error, the mean absolute error, the value it gives, like if I have a model doing that has a mean absolute error of 1 degree, is better than another person's model that is given 2 degrees Celsius error. So yeah, the smaller the error, the better the model. And then the distribution of the errors also matter. Okay, so I think we're coming close to the end. Yeah, so just for the sake of curiosity, for people that would be interested to do something quick with machine learning, at least maybe if you've not done so before, to run your first neural network training code. I put this is a sample neural network training code. Like I simplified it. This is not like actually what we use, but I simplified it for just quick running. And I have a sample data, which I will show in the next slide. So this sample data, I called it sample data, like this just the name of the data, the section of the globe where the data is gathered from. So, but this is the name of the file. So this line in MATLAB reads the data. So it fetches the data from that file. And then in this line, I've told it that the inputs for the data are columns 1 to next to the end, and then the target is the last column. Let me show the data before I come back to this. Yeah, so this is the sample data I'm using here, which I can also share. I have a very small sample that someone can run with this neural code on MATLAB and maybe have a feel of what it looks to train a neural network system. So yeah, this is the sample data we arranged. We actually got this data. It's a radio occultation data for temperature. Yeah, it's a temperature data. So this is the last column is our temperature, which is the target or output for the system. Then these are the inputs, these other 6 columns, 1, 2, 3, 4, 5, 6. Yeah, the first 6 columns are the input column that tell it about the year, the day of the year, hour, altitude, latitude, and longitude, from which it's supposed to learn how the temperature varies. So that's what this code. So here I'm just telling it which columns are the inputs, which is the first 6 columns. N-1 tells it to exclude the last column. Then the target is the end, that's the last column of the data. Then I didn't have time to talk about the number of hidden neurons, but here we have assumed to be 10. In the real world, we normally try a number of hidden layers. So it's something like trial and error to get what value optimal is. One of the parameters I told you we do hyperparameter tuning. So you try to see if the error decreases by using a different number of hidden neurons. So here we are setting aside data for testing, for validation, and for the actual training. Here we are telling it the algorithm to use. These are some things in neural network that the short time for this course will not allow me to talk more about in details. And then, yeah, so here we are now training. The actual line that does the real training is this first line here. So it's the actual code in MATLAB that does the neural network training using the inputs and the targets. And then here we are testing the data sets to produce the RMSEs from them. And this line is saving the final. So when you run this code, you're actually going to have the final trained network that will be saved on your computer as trained network. And that is the one that you normally now can use to make a prediction of any new time data that would be supplied. I think this is the last slide, and I see there are a number of questions. Yeah, I have my short questions here, and that's the end. Yeah, so before those short questions, let me take yours. I think I've eaten into your time, but I will be quicker now. So which activation? Okay, I've answered that one. Can it be lower? Okay. Matrix laboratory. Okay, yeah, somebody asked what is MATLAB. Okay, it's a programming language, and somebody answered it here. It's Matrix Laboratory. That's the abbreviation of that language. Maybe some of you may not know, you probably know Python. So just know it's something like Python. Yeah, it's a programming language like Python, if you know Python. Yeah, a language we can use to program. Most of them also do machine learning. Python is very excellent in machine learning. MATLAB is also excellent in machine learning and several other programming languages. But I use MATLAB most of the time. Sometimes, few occasions I've used Python. But yeah, I use MATLAB maybe because I'm used to it. Okay, yeah, Musa says it's on transit. Okay. Yeah, so I think, yeah, that is that for the class, and that is that for this is the end of the
Yeah.
course. Any, yeah, yes,
Thank you so much, Dr. Daniel. This is a very, very interesting lecture, and I'm also happy with the reaction from our participants. Shows they are
thank
following
you.
up, and yeah,
Mm.
you have done a very good job.
Yeah. Do I
Well,
have
I wouldn't know.
1 minute to ask the last questions?
Okay, good.
Okay, thank you. Okay, so yeah, you probably know this, but maybe yeah, you know what the input layer does. The primary role, it's for, yeah, to bring in the inputs. Actual learning happens in the hidden layer. That's the role, she said. And then, yeah, the output layer is to produce the outputs. And somebody just quickly tell me what is the role of the activation function? Yes, anyone?
It handles the modeling, I think.
Yeah, it handles the modeling, but there's something specifically it does to the
It trains
modeling.
the AI neural network to not to think non-linearly or deal with the non-linear situations.
Thank you so much. It introduces non-linearity. Yeah, it brings in non-linearity. Yeah, we can train a neural network without an activation function. Only that neural network will not be able to learn complex systems. So the role of the activation function is to introduce or to help the neural network to learn non-linearity in the system. So it's to introduce non-linearity in the model. And how does the hidden layer affect the number of neurons in the hidden layer? Fewer neurons mean the brain is not adequate. So it can underfit, so it won't learn enough. But when you have excessive neurons, it's also a problem. It means that the brain is too complex. It causes overfitting. In human brain, we say it causes it to cram the data, to kind of memorize the data. And we know cramming is not a good way of learning things, even for human beings. When you cram things, you only know that things you cram off heart. And when they ask you a question, maybe a question is twisted, or you are asked the question of what you've not crammed, you no longer will be able to, you will not answer it accurately. So that problem is also there with neural networks. It's called overfitting. When you use excessive number of neurons, it just makes it to cram the data you are using to train it. But when you give it a new set of data that it has not seen before, it will perform woefully on that data. Thank you so much, Professor Feinberg. I think that is the end.
Good. Thank you so much. We really appreciate you for your time and effort put in putting this lecture together. And yeah, I'm sure FAST4Future is happy with what we have done today. And we do hope that if the program extends to some other time, maybe when we invite you again, you will make out time to be with us.
Yeah, thank you so much.
Thank you.
Thank
and
you.
From our side, some of your friends, Frank Ona is here saying hi to you.
Yeah.
And,
Hi,
Daniel.
Frank.
Yeah,
Yes,
sorry I
Frank.
was late, but at
No
least I caught the last
problem.
part. Yes.
Yeah,
Greetings.
thank you. Yeah,
Yeah,
greetings
thank
to
you.
you too. Thank you. Yeah.
So I think
Yeah.
this brings us to the end of today's session. Yeah, the school will formally close tomorrow by 11 a.m. of West African time. And probably our principal investigator of FAST4Future may be there to address the participants and maybe respond to some of the questions they may have, especially as regards continuing the FAST4Future program. Of course, as I mentioned at the beginning of the school, this may be the last major academic event we will have on this our platform, because FAST4Future is already winding down. But there is hope of an extension, which perhaps the principal investigator may be in a position to highlight on the closing ceremony, which is tomorrow. So on this note, I thank all of you for the active participation, and we hope to have you tomorrow for the closing event. So thank you so much, and bye.
Wonderful.
Thank you. Bye.
Thank you. Thank you. Bye.
Professor.
Thank you very
Thank
much,
you.
Professor. Wonderful
Thank you
lecture.
so